What if there were colossal monsters lurking silently in the universe, capable of swallowing entire stars and warping the very fabric of reality? These giants, hidden in the darkest corners of space, defy everything we think we know about physics and challenge our understanding of existence itself. They are the supermassive black holes, some of the most mysterious and awe-inspiring phenomena in the cosmos. In this video, we will unlock 20 of the most mind-boggling mysteries surrounding these enigmatic cosmic titans. From their puzzling origins and their immense influence on galaxies to the tantalizing theories of their connection to alternate universes, prepare to embark on an adventure that dives deep into the shadowy depths of the universe. Buckle up, because the secrets of supermassive black holes are as thrilling as they are mysterious, and by the end, you may find yourself questioning the very nature of reality. Now turning to the first mystery, what exactly are supermassive black holes? At their core, black holes are regions in space where gravity is so intense that nothing, not even light, can escape their grasp. They form when massive stars collapse under their own gravity, but supermassive black holes take this concept to an unfathomable scale. These cosmic giants can be millions to billions of times more massive than our Sun, making them vastly larger than their smaller counterparts. For comparison, a regular black hole might have the mass of a few suns, while a supermassive black hole could devour millions of them without breaking a sweat. What sets these behemoths apart is not just their incredible size, but also their location. They are typically found at the centers of galaxies, including our Milky Way. Here, they play a vital role in the structure and evolution of their host galaxies, influencing everything from the formation of stars to the movement of gas and matter across vast distances. Their immense gravitational pull acts like an anchor for galaxies, binding their stars together and shaping their cosmic dance. Supermassive black holes remain some of the most intriguing objects in the universe because they embody the extreme ends of physics, where gravity, time, and space stretch to their limits. By studying them, scientists hope to unlock deeper truths about how galaxies form and evolve, and perhaps even uncover the secrets of space and time itself. So, what makes these cosmic colossi so mind-boggling? Stay with us as we dive into the next mystery to explore the puzzling question of how they come into existence in the first place. Moving forward, how do supermassive black holes come into existence? This question has puzzled scientists for decades, as their formation defies simple explanation. One prominent theory is the concept of direct collapse. According to this idea, supermassive black holes could form directly from the gravitational collapse of enormous gas clouds in the early universe. These clouds, containing vast amounts of matter, might have bypassed the usual process of star formation and instead collapsed straight into massive black holes. Such a scenario would explain how some supermassive black holes could have grown so large in such a short time after the universe began. Another leading hypothesis suggests that supermassive black holes originate from smaller black holes coming together. Over billions of years, these smaller black holes could merge, gradually building up mass until they reach supermassive proportions. This process, though slower than the direct collapse theory, also aligns with observations of black hole mergers and the gravitational waves they produce. Despite these fascinating ideas, the truth is that scientists have yet to determine the exact answer. It's possible that both mechanisms, and perhaps even others we haven't considered yet, contribute to the creation of these cosmic giants. The mystery deepens when we observe supermassive black holes in the very young universe, appearing far earlier than these theories can fully account for. Could there be an unknown shortcut to their formation, or are we missing a crucial piece of the puzzle? As we continue to unravel this enigma, let's turn to the next question. What actually happens beyond the event horizon of these mysterious giants? Now turning to the event horizon, often referred to as the point of no return. This boundary marks the critical juncture where the gravitational pull of a black hole becomes so overwhelming that nothing, neither matter nor light, can escape its grasp. But what truly happens beyond this enigmatic threshold? Once something crosses the event horizon, it is irrevocably drawn toward the heart of the black hole, a region astronomers call the singularity. The singularity itself is a concept that defies our current understanding of physics. At this point, all known laws of nature break down. Matter is thought to be compressed into an infinitely small and dense point, where gravity becomes immeasurable and space-time curves to extremes we can scarcely comprehend. Scientists theorize that as anything approaches the event horizon, it experiences a phenomenon called spaghettification, where tidal forces stretch objects into long, thin shapes due to the extreme difference in gravitational pull between one end of the object and the other. Beyond this, however, lies uncertainty. No signals or information can escape from within the event horizon to reach us, leaving its interior shrouded in mystery. Could exotic forms of matter exist in such extreme conditions? Does time itself function differently? These are questions that challenge the boundaries of human knowledge, and attempts to reconcile them often lead to discussions involving quantum mechanics and general relativity. Yet these two pillars of modern physics are still incompatible in the context of black holes, creating a theoretical puzzle for scientists. This unresolved tension makes the event horizon and what lies beyond it one of the most tantalizing mysteries in astrophysics. As we ponder these questions, we arrive at an even more speculative idea. Could black holes serve as gateways to other universes? Let's explore this fascinating possibility next. Moving forward into the realm of speculation, some scientists and theorists propose a truly mind-bending possibility. Could black holes act as gateways to parallel universes? This idea, while purely theoretical, finds its roots in certain interpretations of general relativity. According to these theories, the immense gravitational forces at the center of a black hole might distort space-time to such an extreme that they create a shortcut, or what is often referred to as a wormhole. A wormhole is essentially a tunnel-like structure connecting two distant points in space-time, or even entirely different universes. It's a concept that has fascinated physicists and science fiction writers alike. If such wormholes exist within supermassive black holes, they could theoretically provide a means of traversing unimaginable distances or even accessing alternate realities. However, the idea comes with immense challenges. For one, no direct evidence has been found to prove that wormholes are real. They remain a mathematical solution, not an observed phenomenon. Even if they did exist, the conditions inside a black hole, such as the incredible tidal forces, would likely make any journey through them impossible for even the most advanced spacecraft. Additionally, issues like stability arise. Wormholes, if they are to function, would require some form of exotic matter with negative energy to keep them open, a speculative substance that has yet to be discovered. Despite these limitations, the idea of black holes as interdimensional gateways continues to captivate the human imagination. It challenges us to rethink the boundaries of the cosmos and inspires us to explore the unexplored. And while this concept remains in the realm of theoretical physics, it reminds us of just how much we have yet to uncover about the universe. Could these cosmic giants really hold the key to unlocking entirely new dimensions? While we ponder this, another equally astonishing mystery arises. Why do supermassive black holes dwell at the heart of most galaxies, including our own? Let's delve into this intriguing question next. Now turning to the next compelling mystery, why do supermassive black holes reside at the center of most galaxies? It's a question that has puzzled astronomers and astrophysicists for decades. These cosmic titans seem to occupy the very heart of large galaxies, including our own Milky Way, and their presence is far from coincidental. One possible explanation lies in their role during the formation and evolution of galaxies themselves. Some scientists hypothesize that galaxies may have formed around these supermassive black holes billions of years ago. In the chaotic early universe, massive gas clouds could have collapsed under their own gravity, giving rise to these black holes. As these young black holes grew by consuming surrounding matter, they may have acted as gravitational anchors, shaping the galaxies that formed around them. Another theory suggests a more symbiotic relationship. While galaxies are not born around black holes, their dense centers naturally funnel gas, dust, and even stars toward the middle, providing a steady feast for the black hole. Over time, this process allows the black hole to grow to its supermassive size while simultaneously influencing the structure of its host galaxy. It's a cosmic feedback loop where the black hole and the galaxy evolve hand in hand. Observations have also revealed a surprising connection between the size of a galaxy's central bulge and the mass of its supermassive black hole, a relationship known as the black hole bulge mass correlation. This suggests that black holes play a critical role in regulating galaxy evolution. By emitting powerful outflows of energy, either through relativistic jets or intense radiation, they can heat up surrounding gas and suppress star formation, effectively shaping the galaxy's future. But the ultimate chicken and egg question remains: did these gravitational giants form first, or did the galaxies? The answer is still elusive, and unraveling this mystery is a major goal of modern astrophysics. What we do know is that supermassive black holes are not just passive bystanders in the cosmic dance. They are dynamic participants, influencing the very fabric and destiny of their galaxies. And while their central placement offers fascinating clues about galactic history, it also opens doors to even more complex questions. Speaking of intriguing cosmic entities, let's now take a closer look at the supermassive black hole right in our galactic neighborhood, Sagittarius A*. Now turning to the supermassive black hole at the heart of our own Milky Way galaxy, let's explore Sagittarius A*. This cosmic giant, situated about 27,000 light-years from Earth, has captivated scientists for decades. Sagittarius A* is estimated to have a mass equivalent to over 4 million suns, all compressed into an area smaller than our solar system. Despite its size, observing this enigmatic entity has been a monumental challenge. Shrouded by dense clouds of gas and dust, the center of our galaxy is nearly invisible to traditional optical telescopes. This is why researchers have had to rely on advanced instruments, such as radio, infrared, and X-ray telescopes to study its mysterious nature. Sagittarius A* was first identified in the early 1970s as a strong radio source, but it wasn't until much later that its true identity as a supermassive black hole was confirmed. A breakthrough came in the 1990s when astronomers focused on tracking the orbits of stars near the galactic center. These stars, moving at mind-boggling speeds, revealed the presence of an incredibly massive, compact object, a supermassive black hole. Observations using cutting-edge technology, like the Very Large Telescope and the Keck Observatory, allowed scientists to measure the black hole's mass with remarkable precision by analyzing the motion of these stars. Then, in 2019, the Event Horizon Telescope project achieved an extraordinary milestone, capturing the first-ever image of the shadow of a black hole. While this was not an image of Sagittarius A*, but rather of the black hole in the galaxy Messier 87, it paved the way for further studies of our own galactic core. Observing Sagittarius A* directly remains an enormous technical challenge because of its relatively small size and the fast motion of the matter swirling around it, but astronomers continue to innovate, pushing the boundaries of what is possible. Studying Sagittarius A* is not just about understanding our galaxy's center, it's a window into the behavior of supermassive black holes across the universe. By unraveling its secrets, we gain insights into the formation of galaxies, the dynamics of black hole accretion, and even the fundamental laws of physics. And as we look deeper into the mysteries of Sagittarius Asterisk, another question arises. How could these colossal black holes grow to such immense sizes so quickly in the early universe? With the next phase of the journey in sight, let's dive into one of the most perplexing questions about supermassive black holes. How can they grow so incredibly fast? This mystery becomes even more intriguing when we turn our gaze to the early universe, just a few 100 million years after the Big Bang. During this time, astronomers have discovered the presence of supermassive black holes with masses equivalent to billions of suns. But how could these cosmic giants achieve such staggering sizes in such a relatively short cosmic timeframe? One leading idea involves a phenomenon known as super-Eddington accretion. In simple terms, this refers to a black hole pulling in matter at a rate much faster than what traditional models would suggest is possible. The Eddington limit, a theoretical boundary, represents the balance between the outward pressure of radiation emitted from infalling matter and the inward pull of gravity. However, under certain conditions, it seems black holes can exceed this limit, devouring material at an accelerated pace. Imagine colossal clouds of gas and dust collapsing directly into a black hole, or streams of matter funneling in so rapidly that the usual rules of accretion break down. These scenarios could enable supermassive black holes to grow at astonishing rates. Another possibility involves the formation of massive seed black holes right after the Big Bang. Instead of starting small, these seeds created from the direct collapse of gigantic primordial gas clouds could have provided a head start in mass, allowing rapid growth over time. Additionally, mergers between smaller black holes might also play a role, combining their masses into increasingly larger structures. By analyzing the light from distant quasars, which are powered by some of the earliest known supermassive black holes, astronomers gather vital clues about their growth mechanisms. These quasars shine with almost unimaginable brightness, hinting at the extreme processes taking place as matter falls into the black hole's gravitational grip. Unraveling this mystery is more than just understanding rapid growth. It challenges our understanding of black hole physics and offers critical insights into the evolution of the earliest galaxies. And as we ponder this cosmic riddle, another question beckons. How do these colossal entities influence the very galaxies they inhabit? With the next phase of the journey in sight, let's uncover how supermassive black holes profoundly influence their surroundings, shaping the very galaxies they reside in. These cosmic titans are far from passive. Their immense gravitational forces exert powerful control over the movement of stars and gas within their host galaxies. Imagine a black hole at the center of a galaxy, pulling in nearby matter and creating a dynamic environment where stars orbit at incredible speeds and vast clouds of gas are drawn into its gravitational grip. But their influence doesn't stop there. Supermassive black holes play a key role in regulating star formation. By consuming massive amounts of gas and dust, key ingredients for creating new stars, these entities effectively limit how many stars a galaxy can produce. Additionally, as matter spirals into a black hole, it heats up and generates immense energy. This energy can be released in the form of relativistic jets, powerful streams of charged particles ejected at nearly the speed of light. These jets can travel across hundreds of thousands of light years, sweeping through the galaxy and beyond. Such jets can have a dramatic effect. They can compress, disperse, or even blow away gas, impacting the galaxy's ability to form stars. Picture these jets as cosmic blowtorches, carving out vast cavities in surrounding gas and triggering chain reactions that ripple through the galaxy. Over time, supermassive black holes act as regulators, balancing the growth and activity of their galaxies. The energy they release not only influences their immediate surroundings but also contributes to shaping large-scale cosmic structures. By studying the intricate relationship between supermassive black holes and their galaxies, astronomers hope to better understand the delicate interplay that governs the evolution of the universe itself. And as we contemplate this intricate balance, a captivating question arises. Is there a limit to how large these cosmic giants can grow? With the next phase of the journey in sight, let's delve into the fascinating question: do supermassive black holes have a maximum size? These cosmic giants are already astonishing in their scale, with some reaching billions of times the mass of our Sun. But is there a limit to how massive they can grow? Consider Ton 618, one of the largest black holes ever discovered, estimated to be an almost incomprehensible 66 billion times the mass of the Sun. This behemoth challenges our understanding of how black holes form and grow. Scientists believe that the size of a supermassive black hole is largely determined by the availability of matter in its surroundings. Over time, black holes consume gas, dust, and even stars, steadily growing larger. Yet the question remains, is there a natural ceiling to this growth? Some theories suggest that black holes may self-regulate. As they accumulate mass and emit immense energy, they may begin to disrupt the very material they rely on to grow. For example, the powerful jets and radiation emitted by a feeding black hole can push surrounding matter away, effectively starving it of new material. Other hypotheses propose that cosmic collisions, such as merging galaxies, provide the only pathway for these black holes to reach extreme sizes. When galaxies collide, their central black holes may merge, producing even larger entities. However, even this process may have limits tied to the density of matter in the universe and the time available for such growth. Could Ton 618 represent a theoretical cap, or are there even larger black holes yet to be discovered in the farthest reaches of the cosmos? For now, the answer remains elusive, inviting more investigation and challenging us to rethink the boundaries of these cosmic giants. As we ponder the potential limits of their size, another profound question emerges. What happens when a black hole itself begins to fade away? Let's explore whether these seemingly eternal giants can truly die. As the next challenge unfolds, let's tackle the intriguing question: can black holes, including supermassive ones, truly die? At first glance, black holes seem eternal and indestructible, with their immense gravitational pull swallowing anything that comes too close. Yet, theoretical physics offers a surprising twist. According to the groundbreaking work of physicist Stephen Hawking, black holes may slowly lose mass over time through a process known as Hawking radiation. This radiation arises from quantum effects near the event horizon, where particle-antiparticle pairs form. In rare cases, one particle escapes while the other falls into the black hole, effectively causing the black hole to lose a tiny amount of mass. This process is incredibly slow for massive black holes, making their evaporation nearly impossible to observe within the current age of the universe. For small black holes, this process could theoretically accelerate near the end of their lifespan, eventually leading to a dramatic and complete evaporation. However, for supermassive black holes, the timeline for this process spans unfathomable durations, trillions upon trillions of years. While fascinating, the concept of black hole death remains purely theoretical, as no such event has ever been observed. More so, some scientists question whether additional mechanisms or unknown physics may come into play before a black hole completely fades away. Could there be remnants left behind, or does the black hole vanish entirely, leaving no trace? As we grapple with these questions, we're reminded that black holes are as mysterious in their potential demise as they are in their existence. With this in mind, we now turn to another captivating aspect of their behavior: the extraordinary phenomenon of black hole mergers. With the next phase of the journey in sight, let's unravel the awe-inspiring phenomenon of black hole mergers. Picture two titanic black holes locked in a cosmic dance, spiraling closer and closer together over millions or even billions of years. As they orbit each other, they lose energy in the form of gravitational waves, ripples in the very fabric of spacetime itself. These waves, predicted by Albert Einstein's theory of general relativity and first detected in 2015, carry immense energy traveling through the universe at the speed of light. When these black holes finally collide and merge, the event releases an astonishing amount of energy, briefly outshining all the stars in the observable universe combined. The final product is often a larger, more massive black hole, accompanied by a burst of gravitational waves that can be detected by instruments here on Earth, like the Laser Interferometer Gravitational Wave Observatory. Black hole mergers are not just extraordinary displays of celestial power, they are also essential tools for scientists, providing a unique way to study the behavior of gravity under extreme conditions. These events help us understand the life cycles of black holes and the environments in which they reside. What's more, they open a window into questions about the nature of space-time and whether our current understanding of the universe's laws holds true under such immense forces. As we marvel at these cosmic collisions, we are reminded of the dynamic and ever-changing nature of the universe. But the story of black holes doesn't end here. Up next, we explore the origins of the largest of these cosmic titans, ultramassive black holes. As the next challenge unfolds, we dive into the staggering mystery of ultramassive black holes, true behemoths of the cosmos that dwarf even the largest supermassive black holes. These colossal entities, with masses often exceeding 10 billion times that of our Sun, pose one of the most intriguing puzzles in astrophysics. How do such giants come into existence? Scientists have proposed several fascinating pathways. One possibility is runaway accretion, where the black hole rapidly grows by devouring vast amounts of surrounding gas, dust, and even entire stars over a relatively short timescale in cosmic terms. Another compelling theory involves galactic collisions. When two massive galaxies collide, their central supermassive black holes are likely to merge, while the chaotic gravitational interactions funnel even more matter into the black hole, accelerating its growth to unimaginable scales. An extraordinary example of an ultramassive black hole can be found at the core of the galaxy Homburg 15A, a galaxy that lies more than 700 million light-years away. The black hole at its center is estimated to weigh an astonishing 40 billion times the mass of the Sun, making it one of the largest known. These cosmic giants challenge our understanding of black hole formation and growth. Could they really grow this massive solely through mergers and accretion, or are there unknown processes at play? Perhaps they started as supermassive black holes in the universe's infancy and have been accumulating matter ever since. Whatever the answer, ultramassive black holes hold the key to unlocking more secrets about the growth of galaxies and the history of the universe itself. As we ponder their origins, let's turn our focus to another awe-inspiring phenomenon, the enigmatic high-energy streams of matter known as black hole jets. As the next phase of the journey comes into view, we turn our attention to one of the most breathtaking displays of raw energy in the universe, black hole jets. These extraordinary streams of matter and energy are expelled from some supermassive black holes at velocities approaching the speed of light. But how can something as infamous for its gravitational pull as a black hole, from which not even light can escape, launch such high-energy jets into the cosmos? The secret lies in the region just outside the black hole itself. When gas, dust, and other matter fall toward a supermassive black hole, they do not plunge directly into it. Instead, they swirl around in what is called an accretion disk, a spinning structure of superheated material that emits immense amounts of energy. Magnetic fields generated by the rotating matter in this disk are thought to play a pivotal role in the formation of these jets. As the intense forces interact, some of the matter near the black hole is ejected along its rotational axis in concentrated streams at nearly the speed of light. These jets are not only composed of particles but also carry high-energy radiation such as X-rays and gamma rays. What makes these jets even more astonishing is their sheer size and impact. Stretching across vast distances, sometimes spanning thousands or even millions of light years, they can influence the galactic environment far beyond the black hole's immediate vicinity. Scientists can detect the energetic signatures of these jets from across the universe, making them crucial tools in studying the behavior of black holes and the role they play in their host galaxies. Yet the exact mechanisms behind black hole jets remain a mystery. How do the magnetic fields shape and accelerate these streams to such extreme speeds? What determines the strength and reach of these powerful outflows? These questions continue to captivate astrophysicists. And as we marvel at the astonishing phenomena of black hole jets, our cosmic journey now shifts toward a question that has intrigued minds for decades. Could these cosmic titans distort the very fabric of time? Now turning to the fascinating concept of time itself, supermassive black holes may hold the key to one of humanity's most mind-bending questions. Could these cosmic giants enable time travel? To explore this, we must first understand the phenomenon known as time dilation. According to Einstein's theory of general relativity, massive objects like supermassive black holes warp the fabric of space and time around them. This effect is so extreme near a black hole that time itself slows down dramatically for an observer close to it compared to someone farther away. Imagine an astronaut approaching the event horizon, the boundary beyond which nothing can return. To an outside observer, the astronaut's actions would appear to slow down, almost as if frozen in time, while for the astronaut, time would pass normally. This bizarre effect suggests that supermassive black holes are not only regions of immense gravitational pull, but also realms where the flow of time becomes distorted in ways we struggle to comprehend. But could this concept of time dilation be harnessed for time travel? Theoretically, if someone were to orbit a supermassive black hole without crossing its event horizon, time for them would pass much slower relative to those far from the black hole. For instance, a few hours near the event horizon might correspond to years or decades in the outside universe. This idea, while intriguing, remains purely theoretical. The extreme conditions near a supermassive black hole, including intense radiation and tidal forces that could rip apart any spacecraft, make it nearly impossible to imagine such a journey with our current technology. Yet, this doesn't stop scientists from pondering the possibilities. Could advanced civilizations one day develop technology capable of navigating these perilous environments? Could we use the gravitational forces of supermassive black holes to study the nature of time, or even to revisit the past and glimpse the future? While these ideas remain in the realm of speculation, they fuel our imagination and drive the quest for deeper understanding. As we ponder the mysteries of time and gravity, let's move forward to another profound question. What lies within the heart of these enigmatic cosmic giants? Moving forward, let's dive into the heart of the enigma. What lies inside a black hole? For decades, this question has puzzled scientists and inspired countless theories. At the center of a black hole lies what is known as a singularity, a point where gravity becomes infinitely strong and the known laws of physics break down. Here, matter is crushed to an unimaginable density. Everything that crosses the event horizon, from stars to gas clouds, is thought to be compressed into this infinitely small space. But the concept of a singularity is where our understanding falters. The idea of infinite density suggests that current models of physics, including general relativity, are incomplete when describing such extreme conditions. Some scientists speculate that within the singularity, entirely new states of matter might exist, forms so exotic that they defy our current comprehension. Could there be something beyond atoms, quarks, or even the most fundamental particles we know of? Or could the singularity be a portal to deeper layers of reality that we've yet to uncover? The mystery grows even more profound when we consider theories that attempt to unify quantum mechanics and gravity. These suggest that singularities might not be infinitely dense after all, but may instead have a finite structure governed by yet-to-be-discovered quantum laws. However, without the ability to observe or directly study a black hole's interior, concrete answers remain out of reach. This unknowable core challenges the boundaries of science and reminds us how much of the universe remains a mystery. As we grapple with the question of what lies in these hidden depths, it's worth considering the next puzzle. How did we even come to discover the existence of these colossal cosmic entities? Now turning to the fascinating story of how we first detected these supermassive black holes, it all began with indirect clues scattered across the cosmos. Decades ago, astronomers noticed peculiar movements of stars near the centers of galaxies, including our very own Milky Way. These stars appeared to be orbiting around an invisible yet incredibly massive object, something that couldn't be explained by any known celestial body at the time. By studying their velocities and trajectories, scientists inferred the presence of an enormous gravitational force, one so immense that it could only be a supermassive black hole. These early observations laid the groundwork for our understanding, sparking curiosity and pushing the limits of technology. Fast forward to a groundbreaking moment in 2019, when humanity witnessed a monumental achievement in black hole research. Using the Event Horizon Telescope, an international collaboration of scientists captured the very first image of a supermassive black hole located at the center of the galaxy Messier 87. This iconic image revealed the glowing ring of light surrounding the shadow of the black hole, providing direct visual evidence of these mysterious entities for the first time. It was a feat of both science and engineering, uniting data from telescopes across the globe to form a picture of something once thought impossible to observe. These advancements have transformed our ability to study supermassive black holes, turning theoretical concepts into tangible discoveries. Yet, as extraordinary as this achievement was, it only scratches the surface. With each breakthrough, we uncover new questions and deeper mysteries. This brings us to an intriguing question. Could we ever go beyond mere detection and actually visit a black hole? Let's explore this daring idea next. Moving forward, let's delve into one of the most daring questions of all. Could humanity ever journey to a black hole? While it sounds like the plot of a science fiction movie, scientists have entertained the idea of sending probes or even spacecraft near these cosmic giants to unravel their secrets. However, let's pause to consider the immense challenges such an endeavor would face. First, there's the matter of extreme gravity. As you approach a supermassive black hole, its gravitational pull becomes unimaginably strong, warping space and time itself. Any spacecraft would need to withstand these intense forces without being stretched or crushed, a phenomenon known as spaghettification that occurs near the event horizon, where the pull of gravity is unequal across an object. Then there's the relentless radiation. Supermassive black holes are often surrounded by glowing disks of gas and dust heating to millions of degrees as they spiral inward. This environment emits immense amounts of radiation, which would be lethal to humans and highly damaging to any spacecraft. Shielding against this radiation would require unprecedented advances in materials science and engineering. And let's not forget the tidal forces. As you get closer to a black hole, the gravitational force increases so dramatically that it could stretch and tear apart even the most robust probes. Navigating these hazards would require extraordinary precision and technology far beyond what we have today. Yet, despite these seemingly insurmountable obstacles, the prospect of exploring a supermassive black hole is not entirely out of reach for the distant future. Advanced robotics, radiation-proof materials, and innovative propulsion systems might one day allow us to send unmanned probes to gather data from the edges of these mysterious objects. While human visitation may remain the stuff of imagination, probes could bring back invaluable insights, revolutionizing our understanding of the universe. With all the potential and peril these journeys might hold, It leaves us to wonder just how far can humanity go in pushing the boundaries of exploration. As we ponder this, let's turn to a larger question. How do black holes shape the cosmos on a grand scale? Now turning to the next grand mystery, let's explore how black holes shape the universe itself. Supermassive black holes, often residing at the centers of galaxies, are far more than just cosmic curiosities. They are powerful architects of their surroundings. Their immense gravitational influence can dictate the movement of stars, gas, and even entire star clusters within their host galaxies, but their role goes even deeper. Surrounding a supermassive black hole is often an accretion disk, a swirling collection of gas and dust that falls toward the black hole. As material in this disk heats up to extraordinary temperatures, it emits vast amounts of energy, forming what is known as an active galactic nucleus. These active galactic nuclei can shine brighter than the combined light of all the stars in the galaxy, and even produce high-speed jets of particles that extend for thousands of light years, cutting through space like cosmic lighthouses. These jets can have a profound impact on the galaxy. For instance, they can push away gas and dust that would otherwise form new stars, effectively regulating star formation. This feedback process leads scientists to believe that supermassive black holes play a significant role in shaping the life cycles of galaxies. On an even larger scale, the effects of these black holes ripple through the cosmos itself. Clusters of galaxies are often bound together by supermassive black holes at their cores. The energy released by the black holes can influence the distribution and temperature of the gas within these clusters, impacting how galaxies form and evolve over billions of years. Whether black holes are shaping galaxies or galaxies are nurturing these black holes is still a subject of intense debate in astrophysics. What's clear, though, is that this symbiotic relationship has played a crucial role in crafting the universe we see today. As we begin to understand these dynamics, one thing becomes apparent. Supermassive black holes are not just the silent observers of the cosmos. They are the very forces that sculpt its structure and destiny. With this breathtaking realization, let's journey into another aspect of these colossal entities. Are supermassive black holes truly dark, or do they illuminate the universe in unexpected ways? Now turning to the question of whether supermassive black holes are truly black, we encounter a fascinating paradox. While they are often described as the ultimate voids from which no light can escape, supermassive black holes are far from being completely dark. In fact, when surrounded by an accretion disk, they can become some of the brightest objects in the universe. The intense gravitational pull of the black hole causes gas and dust in the accretion disk to spiral inward, accelerating to incredible speeds and colliding with immense force. These collisions create friction, heating the material to millions of degrees, and as it heats up, it emits immense amounts of energy in the form of visible light, X-rays, and other forms of radiation. This phenomenon is what makes active galactic nuclei so dazzling, sometimes outshining all the stars in their host galaxy combined. But the story doesn't end there. Many supermassive black holes also produce high-speed jets of particles that shoot outward along their magnetic poles, traveling at nearly the speed of light. These jets emit powerful radiation that can be detected across vast cosmic distances, serving as some of the brightest beacons in the universe. It's these luminous components, accretion disks and jets, that challenge the very notion of black holes as merely dark, invisible objects. Instead, they transform black holes into cosmic lighthouses, illuminating the universe in ways that continue to astound scientists. This dual identity as both cosmic darkness and radiant brilliance invites us to reconsider the essence of these enigmatic entities. Are they voids of destruction, or are they also engines of creation? This striking contradiction lies at the heart of our evolving understanding of supermassive black holes. And with this revelation, let's venture into the next profound mystery. Could these cosmic powerhouses ever serve as a source of energy for advanced civilizations? Now turning to the question of whether these colossal cosmic engines could one day be harnessed as a source of energy, we step into a realm of futuristic speculation that borders on science fiction yet remains grounded in intriguing scientific theories. One such idea is the Penrose process, a concept proposed by physicist Roger Penrose. This process suggests that a highly advanced civilization could extract energy from the rotational motion of a supermassive black hole. The method involves strategically placing matter in the black hole's ergosphere, a region just outside the event horizon where space-time itself is dragged along by the black hole's spin. By carefully manipulating this interaction, it's theorized that energy could be siphoned off, potentially powering technologies on an unimaginable scale. But that's not the only possibility. The immense radiation emitted by the accretion disks of active supermassive black holes could also serve as a power source. Imagine vast structures, perhaps resembling Dyson spheres, built to capture and convert this energy into usable forms, providing nearly limitless power to advanced civilizations. While such concepts remain purely hypothetical for now, they challenge us to think about the boundless potential of our universe. Could humanity or another intelligent species one day develop the technology to make these ideas a reality? If so, it would not only redefine our relationship with these mysterious entities, but also unlock an entirely new era of cosmic exploration and innovation. As we ponder these possibilities, it's clear that supermassive black holes, far from being mere agents of destruction, might one day become vital to the survival and advancement of intelligent life, catapulting us into a future where the universe itself becomes a source of infinite energy. Moving forward, the future of black hole research holds the promise of uncovering even deeper secrets about these enigmatic giants of the cosmos. Thanks to groundbreaking advancements in technology, our ability to explore and understand supermassive black holes is evolving at an unprecedented pace. Take, for example, the James Webb Space Telescope, a marvel of modern engineering. With its ability to observe the universe in infrared light, this telescope is uniquely equipped to peer through the dense clouds of gas and dust that often obscure the centers of galaxies where supermassive black holes reside. By capturing detailed images and data, it has the potential to reveal how these colossal objects interact with their surroundings, shedding light on questions of their growth and influence over time. Meanwhile, next-generation gravitational wave detectors are opening an entirely new window into the universe. These instruments are designed to detect the ripples in space-time caused by cataclysmic events, such as the merger of two black holes. By analyzing these signals, scientists can glean valuable information about the mass, spin, and other properties of black holes, including those at the supermassive scale. What makes these tools so revolutionary is not just what they can tell us about individual black holes, but also how they can help map the broader cosmic landscape. Together, they hold the potential to transform our understanding of the role supermassive black holes play in shaping galaxies, influencing star formation, and even sculpting the large-scale structure of the universe itself. As we look to the future, it's clear that these technologies will be instrumental in solving some of the most profound mysteries of our time, pushing the boundaries of human knowledge and bringing us closer to answering the age-old question of what lies at the heart of the cosmos. Now turning to advanced theories about supermassive black holes, we enter a realm of ideas that challenge the boundaries of modern physics, offering glimpses into the most cutting-edge and sometimes controversial aspects of scientific thought. One of the most intriguing questions revolves around the role of quantum effects in black holes. Black holes, as described by general relativity, are regions of space where gravity is so intense that nothing, not even light, can escape. Yet, when we bring quantum mechanics into the picture, things start to get complicated. One such concept, known as Hawking radiation, suggests that black holes may not be as inescapable as they seem. According to this theory, quantum effects at the event horizon, the boundary of a black hole, can cause particle-antiparticle pairs to form. One of these particles can escape into space while the other is pulled back into the black hole. Over immense timescales, this process could theoretically cause black holes to lose mass and eventually evaporate. This idea, while fascinating, raises profound questions about the nature of black holes and the very fabric of the universe. Another advanced theory suggests that black holes themselves might evolve over time, not just in terms of consuming matter and growing larger, but possibly in ways that alter their fundamental properties. Some researchers propose that black holes could transition into entirely different states of existence, perhaps influenced by unknown forces or conditions within the universe. This leads to even more speculative ideas, such as whether black holes might hold clues to a deeper, unified theory that bridges quantum mechanics and general relativity. Could they serve as laboratories for understanding the mysterious link between these two pillars of physics? While these theories remain far from proven, they underscore just how much we still have to learn about supermassive black holes. As we push deeper into these uncharted waters, the possibilities are as tantalizing as they are mind-bending. Moving forward, the mysteries of supermassive black holes prompt us to reflect on what they reveal about humanity's place in the vast universe. These immense cosmic phenomena, with their mind-bending physics and profound complexity, challenge us to rethink everything we know about existence itself. They act as reminders of both the grandeur and the humility of our position within the cosmos. On one hand, studying supermassive black holes inspires awe at the sheer scale and power of the universe, showing us how small and fragile our world really is in the grand scheme of things. On the other hand, it is our ability to unravel even a fraction of their secrets through science and imagination that highlights the incredible potential of human ingenuity. The pursuit of understanding black holes has repeatedly pushed the boundaries of science, leading to groundbreaking advancements in physics, astronomy, and technology. For instance, the effort to capture the first ever image of a black hole united scientists across the globe, resulting in an achievement that was as much a triumph of human collaboration as it was of scientific innovation. Beyond the scientific domain, black holes also provoke deeply philosophical questions. What is the nature of reality? Are there ultimate limits to what we can know and understand? Could exploring these enigmas one day uncover answers to the most fundamental questions about the universe and our existence? These questions remind us that curiosity is one of humanity's greatest strengths, driving us to seek knowledge even in the face of uncertainty. In a way, the study of supermassive black holes teaches us that the mysteries of the cosmos are not obstacles to understanding but rather invitations to explore, discover, and grow as a species. They serve as both a mirror reflecting our intellectual achievements and a gateway to realms of discovery still waiting to be unlocked. Now turning to myths and misconceptions about black holes, one of the most common misunderstandings is the idea that they are cosmic vacuum cleaners, indiscriminately sucking everything into their grasp. While it is true that black holes have incredibly strong gravitational pulls, they are not roaming through space devouring planets and stars. In reality, black holes are just like any other massive object in the universe in terms of their gravitational influence. If the Sun were replaced with a black hole of the same mass, Earth would continue its orbit unchanged. The difference lies in the extreme concentration of mass within the black hole, which gives it unique properties like the event horizon, beyond which light itself cannot escape. Another misconception is that black holes are somehow completely invisible and can never be detected. While it is true that black holes themselves emit no light, they can often be spotted by the effects they have on their surroundings. For example, the intense gravitational pull of a black hole can cause nearby gas and dust to spiral into what is called an accretion disk. As this material accelerates and heats up, it emits brilliant X-rays and other forms of radiation, essentially lighting up the presence of the black hole. Then there is the myth that black holes mark the end of the universe, as if anything crossing the event horizon is gone forever, never to interact with the cosmos again. While it is true that matter and light cannot escape a black hole once they pass the event horizon, their gravitational influence still shapes the universe. Black holes play vital roles in galaxy formation, star evolution, and even the distribution of matter across the cosmos. Finally, some people think that black holes defy all known laws of physics. While they do operate in extreme regimes where our understanding of gravity and quantum mechanics is tested, they are not magical or completely beyond comprehension. Scientists have developed mathematical models that explain their behavior with remarkable precision, and ongoing research continues to explore their mysteries in greater depth. Busting these myths is not just about correcting misinformation, it is about revealing the fascinating truth, which is often even more incredible than the misconceptions. Understanding what black holes truly are and what they are not allows us to appreciate how these cosmic giants fit into the universe's grand story, sparking both wonder and curiosity about the science that unveils their secrets. With the next phase of the journey in sight, let us explore how supermassive black holes have captured the imagination of storytellers in science fiction. These cosmic marvels, with their almost supernatural qualities, have become a favorite subject in movies, books, and games. Take the film Interstellar, for instance, where the depiction of a supermassive black hole named Gargantua was so scientifically detailed that it was created with input from renowned astrophysicist Kip Thorne. The film vividly portrayed concepts like time dilation, where time moves slower near the immense gravity of the black hole compared to elsewhere, a phenomenon rooted in Einstein's theory of general relativity. This brought an abstract scientific idea to life, leaving audiences both entertained and educated. Similarly, black holes have made their mark in literature. Science fiction novels often use their mysterious nature as a backdrop for exploring themes of survival, exploration, and the unknown. Authors imagine scenarios like humans venturing near black holes to harness their energy, or even discovering wormholes hidden within, serving as shortcuts to far-off parts of the universe. These creative takes fuel curiosity about what these cosmic giants might truly be capable of. In the world of video games, black holes provide thrilling settings for players to navigate or escape from. Titles like Elite Dangerous incorporate realistic simulations of supermassive black holes, challenging players to contend with the extreme gravitational forces while exploring virtual galaxies. These portrayals not only entertain but also subtly educate, embedding real scientific principles into pop culture. By appearing in these forms of media, supermassive black holes have become more than just scientific phenomena. They have entered the public consciousness as symbols of mystery, power, and possibility. These stories spark wonder and provoke questions about the universe, inspiring viewers, readers, and gamers to learn more about the real science behind the fiction. And as accurate as some portrayals may be, they also leave room for imagination to soar, reminding us of how much more there is to discover. From cinema screens to the pages of books and the digital worlds of games, these depictions help bridge the gap between complex astrophysics and everyday curiosity. As the journey through these fascinating mysteries of supermassive black holes comes to an end, one truth remains abundantly clear. These cosmic giants are as enigmatic as they are awe-inspiring. From their mind-bending formation and incomprehensible size to their influence on galaxies and their depiction in popular culture, supermassive black holes challenge the boundaries of human understanding at every turn. They are gateways to questions that extend far beyond the cosmos, touching on the very nature of reality and our place within it. What secrets still lie hidden beyond the event horizon? Could they connect us to other universes or serve as keys to harnessing untold energy in the distant future? The mysteries we have explored today remind us that while our knowledge of the universe has grown immensely, there is so much left to uncover. Let the allure of these celestial wonders continue to spark curiosity and inspire new discoveries in the years to come. If this journey has left you with questions, theories, or favorite mysteries, we want to hear from you. Share your thoughts in the comments below and let's continue this cosmic conversation together. And before you go, don't forget to like this video, share it with fellow space enthusiasts, and subscribe to our channel for more incredible explorations of the universe. Hit that notification bell so you'll never miss another cosmic adventure. Until next time, keep looking up and wondering what lies beyond.